Students, in our previous videos, our topic of discussions were the limits of functions of two variables and continuity of function of two variables. Now, the next step in our discussion, next topic of our discussion is derivatives. Once we have defined limit and continuity, now it's time to discuss about the differentiation of functions of several variables, or in particular functions of differentiation of functions of two variables. So once a function becomes differentiable, that function is most useful one, and if it is not differentiable, it will not have the use as we think, or we cannot use those functions which are not differentiable. So the main point of our discussion from here on, from this class onwards, will be differentiation, its properties and its applications of functions of several variables, and in particular functions of two variables. Now, before going to the definition of differential of a function of two variables, I just want to remind you about the definition of differential of single variable. Now, consider the function y equal f of x. Now, the derivative of f of x is usually denoted as dy by dx or f dash x, and it is defined in terms of a limit, and it is defined as f dash of x naught, the derivative of f of x at x naught, equal to limit h tends to 0 f of x naught plus h minus f of x naught divided by h, or in the sense derivative, by derivative we measure, or the meaning of derivative is the rate of change of f with respect to the change in x in the case of single variables. That means if the variable x changes, then obviously the function will change, the value f of x will change, and we are measuring the rate of change of that function. And this is the definition, this limiting case is the definition of derivative of function of single variable. If this limit exists, we say that the function is differentiable, and the value of this limit is generally called, or is called, the derivative of f of x at the point x naught. Now, in this case, there was only a single variable. Now, what happens when we extend this definition, or when we go to the case of two variables? That is, you are given a function z equal to f of xy, and f of xy contains two variables. Now, here also we can differentiate, but the differentiation in the sense is somewhat different, or we won't have the permission, or we don't have the priority to differentiate or define the full derivative. In certain cases we can define the full derivative, but since there are two variables, we define the derivative as partial derivatives, or we are considering among two variables, we are considering one variable as constant and differentiating with respect to the other. At a time, we are only considering one variable as variable, and we are taking the other variable as a constant. So, in such cases, we don't have the total differential, or we rather define the partial differential or partial derivative. Now, in the case of single variable, this f dash of x naught denoted the rate of change of f of x with respect to the variable x. Now, in the case of f of xy, as there are two variables, we can measure the rate of change of f of xy with respect to x alone, or we can only measure the rate of change of f of xy with respect to the single variable x and separately, and we can measure the rate of change of f with respect to the variable y alone. Such differentials are called partial differentials. And in general, those partial differentials are denoted as dou z by dou x, or partial differential of z, dou z by dou x equal to dou f by dou x. This denotes the partial differential of f with respect to x alone. And dou z by dou y, or dou f by dou y, as z equal to f of xy, we take dou z by dou y, or we write dou z by dou y equal to dou f by dou y. And this is the partial derivative of f of xy with respect to y alone. And in the case of dou f by dou x, the only variable we are considering is x, and we take y as constant. And in the case of dou f by dou y, the variable we are considering is y, and we take x as constant. So we are going to define these two partial differentials. And if w equal to f of x, y, z, or f is a function of three variables. Similarly, we can define dou f by dou z, which is discussed in one of our problems later in this class. Now, I'm going to define, I have a point x naught y naught. I'm going to define the partial derivative of f with respect to x alone at the point x naught y naught. It is denoted as fx x naught y naught. Fx x naught y naught equal to dou f by dou x at x naught y naught. Dou f by dou x at x naught y naught. That is rate of change of f with respect to x alone at the point x naught. So you can compare this with the original definition of limit of function of single variable. Here we have only one variable and we are finding the rate of change of f with respect to that particular variable. Here we have two variables, still we are considering one variable as a constant and finding the rate of change of f with respect to the other variable. Now dou f by dou x means we are differentiating f with respect to x alone by considering y as a constant. So dou f by dou x measures the rate of change of f with respect to x alone. So the change takes place only in the single variable x and y at y naught is kept as a constant. So according to this definition, I can write dou f by dou x at x naught y naught, rate of change of f with respect to x alone at x naught, that is limit h tends to 0, f of x naught plus h y naught. You can compare with the original definition. Here only there was one variable x naught plus h, but here one more variable is there, y naught. So I am keeping y naught as a constant or y as a constant. So the change takes place only in the variable x. So limit h tends to 0, f of x naught plus h y naught minus f of x naught y naught divided by h. Rate of change of f with respect to the variable x alone. Only the variable x is changing. So y at y naught is kept as constant. So this is a definition of dou f by dou x at the point, at the two tuple at the point x naught y naught. Limit h tends to 0 if the change takes place only in x. So limit h tends to 0, f of x naught plus h y naught minus f of x naught y naught divided by h. Similarly, f y x naught y naught is a partial derivative of f of x y with respect to y alone. Or we are finding the rate of change of f with respect to y alone at the point x naught y naught. So we are in effect keeping the point x naught as a constant and we are changing only y. And in that case we get the partial derivative of f with respect to y alone as dou f by dou y at x naught y naught equal to limit h tends to 0, f of x naught y naught plus h. You have to understand the difference here. In the case of dou f by dou x, the change is taking place only in the value of x. So we have written f of x naught plus h and y naught is kept as y is kept as a constant. But in this case, the change is taking place only in the variable y, and at the same time I am keeping x as a I am considering x or x naught x as a constant variable. So no change takes place in the variable x. So dou f by dou y equal to limit h tends to 0, f of x naught y naught plus h, change takes place in y, minus f of x naught y naught divided by h. So this is a definition for dou f by dou x and dou f by dou y. If f has three variables, say f of x, y, z, in the same way we can define dou f by dou z. And I am not going to the details of that function because it is quite difficult to write this in the case of three variables. But this is a formal definition of differential, partial differential of function of two variables. This is a formal definition. And remember that in most cases we won't be using this definition. Once the function is deemed or defined to be differential, found to be differentiable, the function of two variables f of x, y, z be differentiable, we are not using this particular definition, but we rather use the definition of original function of differentiation of function of single variable. The only thing is that if we are differentiating with respect to x, we take y as a constant. Most of you may have studied this type of differentiation in your +2 classes. So actually this is a formal definition, and while doing problems we don't use most often we don't use this definition, but rather we use the formula for differentiation of single variables, because actually we are doing only differentiating only with respect to a single variable. So we can apply all those formulas for differentiation of single variables in the case of double variables also. Sum rule, product, everything can be applied in this case. The only thing is that we keep one variable constant and differentiate the function with respect to the other variable, which is evident from these two problems. These are two simple problems, and actually our topic is not this one. This is just an introduction, and from this topic we are going to the other topics like linearization, Laplace's equation. These topics are all which you have studied in the +2 classes or previous semesters. So we will, just for the sake of reminding or revision, we will be doing one or two problems of partial derivatives, then we straight go to the other topics of differentiation like linearization, Laplace's equation and all. Now remember that once we are finding or we are differentiating f with respect to x alone, we take y as a constant and we apply all the known formula of differentiation of single variables. Now we take one such problem: find dou f by dou x and dou f by dou y at 2 minus 1 given f of xy equal to 3x cubed y plus 4xy square minus 2x plus 4y minus 5. Now this is a function of two variables, x and y. There are two variables, x and y. We have to find dou f by dou x at 2 minus 1, differential of f, partial differential of f with respect to x at 2 minus 1, and similarly dou f by dou y at 2 minus 1. Now f of xy equal to 3x cubed y plus 4xy square minus 2x plus 4y minus 5, the same function. Now dou f by dou x. What do you mean by dou f by dou x? Dou f by dou x, once we are going to find, and if we are finding dou f by dou x, we take x as the variable and keep y as a constant. This is a simple problem, and this is a simple result also. Now dou f by dou x, we are differentiating f with respect to x alone. Y is a constant. Now if you differentiate this, the first quantity with x alone, you take y as a constant. So differentiating this, 3x cube y, the differential of 3x cube is 3x square. But differential of this one is that the differential of 3x cube y is 3 into 3x square into y, that is 9x square y plus 4xy, differential of 4xy square. Here y is a constant. Only the variable is x. So its differential is 4y square. So 9x square y plus 4y square and here the third term is minus 2x. Its differential is minus 2. Minus 2x, differential of minus 2x is minus 2. 4y, it is a constant because we are differentiating with respect to x alone, so this differential of this is 0, and minus 5 is obviously a constant, its differential is also 0. So you get dou f by dou x as 9x square y plus 4y square minus 2, and dou f by dou x at 2 minus 1 is, you substitute x and y in this expression, you get it as minus 34. So dou f by dou x is this one. Dou f by dou x at 2 minus 1 is minus 34. Just ordinary differentiation. The only thing is you have to remember is that we are taking y as a constant and differentiating only with respect to x. Now similarly dou f by dou y. Dou f by dou y equal to differentiate this function with respect to y alone. So y is a variable and x is a constant. So dou f by dou y, differential of this is 3x cube. Y is a variable, x is a constant. So 3x cube is a constant and y is only variable. So dou f by dou y equal to 3x cube. Here it is 8xy. The differential of y square is 2y and 4x. So 8xy, 4x into 2y, that is 8xy. Here it is, differential is 0 because x is a constant, since we are differentiating with respect to y. Here the differential is simply 4 and here the differential is 0. So dou f by dou y equal to 3x cube plus 8xy plus simply 4. And dou f by dou y at 2 minus 1. Substitute the values of x and y in this expression. You get dou f by dou y at 2 minus 1 as 12. So this is the method of finding partial derivative of functions with respect to x and y. We will do one more problem because this is a simple, these are all simple things and we don't have, I think there is no requirement that we spend such a lot of time solving such simple problems, we will pass on to the other topics which are new to students or new in this 5th semester. All these topics we have studied earlier. Now one more problem we will do regarding or that depicts the partial differentials. Now 2. Find fx fy if f of xy equal to 2y by y plus cos x. If f of xy equal to 2y by y plus cos x, find fx and fy. Here you have to use this result. Differential of f by g, d by dx of, or d by dy, anything. D by dx of f by g equal to f dash g minus g dash f divided by g square. The only thing is that in the case of partial differential, this d by dx we differentiate with respect to x alone by keeping y as a constant. This differential becomes partial differential. All the results of differentiation of single variable can be applied here. So if d by dx of f by g is f dash g minus g dash f by g square, dou by dou x can be found out in a similar manner. The only thing is that we consider y as a constant, so we can apply this result. Now fx equal to dou f by dou x. Dou f by dou x means here f dash g minus g dash f dash, our f dash, f is 2y, here f is 2y, f equal to 2y and g equal to y plus cos x, g equal to y plus cos x. So f dash g minus g dash f, here f dash means dou f by dou x and g dash means dou g by dou x. So f dash g, f dash means it is 0, g 0 into g is again 0. F dash g minus g dash f. G dash means dou g by dou x. Dou g by dou x is minus sin x. So g dash f minus sin x into f. F dash g minus g dash f. F dash g is 0 minus g dash is minus sin x and f is 2y. So dou f by dou x equal to 0 minus 2y into minus sin x divided by g square. G square is y plus cos x whole square. So this simply reduces to 2y sin x divided by y plus cos x whole square. The only thing is that we have considered y as a constant and just applied this particular result and simply changed d by dx to dou by dou x. That's all. Now fy of dou f, fy is dou f by dou y. Dou f by dou y here we change the variable to y, that is dou by dou y of f by g is f dash g minus g dash f by g square, where f dash is dou f by dou y and g dash is dou g by dou y. This is the only difference. Now dou f by dou y equal to f dash means dou f by dou y. Dou f by dou y is 2, f is 2y, dou f by dou y is 2, f dash g means 2 into y plus cos x minus g dash f. G dash means dou g by dou y, that is simply 1. Cos x is a constant with respect to, as we are differentiating with respect to y alone, this is a constant, its differential is 0. So dou g by dou y is simply 1. So 2 into y plus cos x minus 1 into 2y, g dash f, g dash is 1, f is 2y, minus 1 into 2y divided by y plus g square, that is y plus cos x whole square. Now you can simplify this and you get the numerator as 2 cos x, 2y get cancelled, 2 cos x divided by y plus cos x whole square. Now so this is our second example. We have found out dou f by dou x and dou f by dou y using the rule d by dx of f by g is f dash g minus g dash f by g square. The only thing is that we are applying partial differentiation in the case of in the place of d by dx. That is the only difference. And the difference between total differentiation and partial differentiation is that in the case of partial differentiation, if we are differentiating with respect to x, we consider x as a variable and keep y as a constant. If we are differentiating with respect to y, we consider y as a variable and keep x as constant. All other rules of differentiation are applicable in the case of partial differential also. So these are two simple problems regarding partial differentiation. In the coming classes, we will be applying the technique of partial differentiation in so many problems. So I don't feel that doing problems regarding partial differentiation alone is that important. We will be applying this theorem, this theory or this result in the coming problems like linearization, Laplacification, all the further coming problems will be using this partial differentiation. So there are so many problems available for practice regarding this partial differentiation. You can check the literature or textbooks to get further problems. You can practice it. Now I am going to the next topic of linearization. Now what is the definition of linearization? What is the purpose of linearization? The main purpose of linearization is that to simplify the given function so that it can be differentiated or it can be understood in a much simpler manner. You can linearize many functions which are complicated functions and you get a linear form of the function. Actually this is an approximation. A linearization is an approximation of an original function, and in most practical problems this approximation may yield very good, very powerful results. So we are not going to the applications of such problems. We are going to define what is the definition of linearization, and we are simply doing two problems. And the main purpose of linearization is to simplify the given function into a linear form so that mathematical operations are much more simpler, and the linearized function will almost have the same property or will almost show the same result as that of the original function in many practical problems. Anyway, I am going to define linearization of f of xy. A linearization of f of xy, function of two variables f of xy at x0, y0, is a function L of xy which is given as L of xy equal to f of x0, y0 plus x minus x0 fx x0, y0 plus y minus y0 fy x0, y0. So you are given a function of two variables f of xy, and you have to find the linearization of f of xy, or you want to convert the function to a linear function or approximate this function f of xy as a linear function at the point x0, y0. And the linearization or linear functions obtained is given by the formula, or it is obtained by the formula L of xy equal to f of x0, y0 plus x minus x0 into fx x0, y0, that is dou f by dou x x0, y0 at x0, y0 plus y minus y0 into fy x0, y0. Now if we extend this definition to three variables, or if we have to find the linearization of f of x, y, z, the only difference is you will get one more term, and the linearization will be L of x, y, z. I have done in the second problem. The linearization will be L of x, y, z equal to f of x0, y0, z0 plus x minus x0 into fx x0, y0, z0 plus y minus y0 into fy x0, y0, z0 plus one more term will be there, z minus z0 into fz x0, y0, z0. This is the only difference between the linearization of function of two variables and linearization of function of three variables. You have to by heart this formula. You don't have to check the approximation, how much valid is this approximation. That is not in the syllabus. You just have to remember this formula, and we will do two problems. One problem is the linearization of function of two variables. The second one is linearization of function of three variables. Here I have not written the formula for linearization of three variables. It will be stated in this particular problem. Now our first problem is find the linearization of e raised to x cos y at 0 pi by 2. So here the f of xy is e raised to x cos y. It is a function of two variables, and the point at which we have to find the linearization is 0 pi by 2. Now you can compare with this formula to find the linearization. You have to obtain these quantities, f of x0, y0, fx x0, y0, fy x0, y0. All these quantities have to be found out, and you have to substitute in this equation. So we will find it one by one. We will calculate it one by one. Now f of xy equal to e raised to x cos y. x0, y0 is 0 pi by 2. So f of x0, y0 is f of 0 pi by 2. f of x0, y0 is f of 0 pi by 2 equal to e raised to 0 cos pi by 2 equal to 0. Now fx of xy, fx, the partial derivative of f with respect to x, fx of xy is, you have to differentiate this with respect to x alone. So y is constant, cos y is constant. The only variable is x, and the variable function is e raised to x. So fx xy is e raised to x cos y itself. Differential of e raised to x is e raised to x itself. So fx xy equal to e raised to x cos y, and fx x0 y0, fx x0 y0 is fx 0 pi by 2. That is again e raised to 0 cos pi by 2, which is 0. Okay, so fx xy or fx 0 pi by 2 is again 0 itself. One more quantity is to be found out, that is fy. Fy of xy equal to, now I have to differentiate this with respect to y alone. I am considering x as a constant. So e raised to x will be a constant. The only function I have to differentiate is cos y. So differential of cos y is minus sin y. So fy xy is e raised to x into minus sin y, that is minus e raised to x sin y. Fy x naught y naught is fy 0 pi by 2, that is minus e raised to 0 sin pi by 2 is minus 1. So I have found out all the quantities. F of x naught y naught is f of 0 pi by 2, that is 0. Fx x naught y naught is fx 0 pi by 2 is again 0. Fy x naught y naught is fy 0 pi by 2 is minus 1. I am substituting these quantities in the formula for linearization, and you get L of xy equal to f of 0 pi by 2 plus x minus x naught. X minus x naught is x minus 0 because x naught is 0. X minus x naught fx 0 pi by 2 plus y minus y naught. Y naught is pi by 2. Y naught is pi by 2. So y minus y naught fy 0 pi by 2. Fy x naught y naught fy 0 pi by 2, that is 0 plus 0 plus y minus pi by 2 into minus 1. Y minus pi by 2, this is minus 1. I have calculated this. This is minus 1. So 0 plus y minus pi by 2 into minus 1, that is pi by 2 minus y. You can see the difference. This was a bit complicated function which includes exponential function and trigonometric functions. Now its linearization is pi by 2 minus y. This is much simpler function. It does not have powers of y square, x square, etc. So this function is much more easy to operate, and almost this will be a vague approximation of the given function. I am not going to details of such approximations. Now this is the linearization of e raised to x cos y up to the point 0 pi by 2. Now our second problem in the topic linearization is a function of three variables, that is f of x y z equal to xz minus 3yz plus 2, and I have to find the linearization at 1, 1, 2. So this is my function, and I have to find the linearization at the point 1, 1, 2. Now you have to know the formula in the case of three variables. The formula is, I am just extending this. L x y z, that is linearization, is f of x naught y naught z naught plus x minus x naught into fx x naught y naught z naught plus y minus y naught into fy x naught y naught z naught plus z minus z naught into fz x naught y naught z naught. So this is a mere extension of linearization formula for the function of two variables. Only the term involving z is augmented. So we have to find f of x naught y naught z naught, fx x naught y naught z naught, fy x naught y naught z naught, and fz x naught y naught z naught. Then we have to substitute all these quantities in this expression to get the linearization. Now we will start from the beginning, that is f of x y z. F of x y z equal to xz minus 3yz plus 2. F of x naught y naught z naught equal to f of 1, 1, 2. This is my point, x naught y naught z naught. F of x y z equal to xz minus 3yz plus 2. F of x naught y naught z naught equal to f of 1, 1, 2. Substituting in this, you get this as minus 2. Now next term is this one, fx x naught y naught z naught. Now fx x y z, fx x y z, dou f by dou x. Here you are differentiating this function with respect to x alone. You will be getting, so y and z both are constants. So fx x y z is simply z itself. All other terms becomes 0 once you differentiate with respect to x, because this does not contain x. This also is a constant. Y and z are constants if you are differentiating with respect to x. So the only differential remaining is z. Now fx x naught y naught z naught equal to fx 1, 1, 2 is simply 2 itself, because it is z. F of fx x y z is z. So fx 1, 1, 2 is simply 2. Now fy of x y z, I am differentiating this with respect to y alone. So x and z are constants, 2 is a constant. The only differential we will be getting, non-zero differential we will be getting, is this one, the differential of this, and the differential of this is minus 3z. So fy x y z equal to minus 3z. Fy x naught y naught z naught equal to fy 1, 1, 2 equal to minus 6. Just substitute z equal to 2 in this expression. So fy112 equal to minus 6. Similarly, fz xyz, we are differentiating f with respect to z alone, or we are considering x and y as constants. So fz xyz equal to, let us check the differential of this one, that is fz with respect to z alone. So here it is x, here it is minus 3y. So fz xyz is x minus 3y. fz xyz is x minus 3y. And fz x0 y0 z0 equal to fz 112. fz 112, that is, simply you can substitute and find the value as fz 112 as minus 2. fz 112 as minus 2. Just substitute these values, 1 1 in this expression, 1 1, 1 minus 2, or 1 minus 3, that is minus 2. So fz xyz is minus 2. Now we have found out all these values, that is f of x0 y0 is z0, fx of x0 y0 is z0, fy of x0 y0 is z0, and fz of x0 y0 is z0. All those we have calculated. Now you can substitute these values in the expression for L of xyz. And on substitution we get this, L of xyz equal to minus 2 f of x0 y0 is z0 minus 2 plus x minus x0, x minus 1 into fx of x0 y0 is z0, that is 2 minus 2 plus x minus 1 into 2 plus y minus 1, y minus y0, that is y minus 1 into fy, that is minus 6. So y minus 1 into minus 6 plus z minus z0, z minus z0 is z minus 2, z0 is 2. So z minus 2 into fz, that is minus 2 itself. So on simplification, you can expand the brackets and simplify. You get L of xy is equal to x minus 6y minus 2z plus 6. So this is the linearization of the function of three variables f of x, y, z as given as this. So these are two sample problems. The first one contains two variables, second one contains three variables. Just you have to find all these quantities. The only thing that you have to know is how to differentiate partially and this formula. Simple result, just differentiation and substitution, nothing other than that. So I will be stopping linearization here in this video itself. In the next video I will be passing on to the other topic. I think it is Laplace's equation. So lots and lots of problems are available in your textbook, or you can find in the question papers also problems that asking about linearization. So all these are simple things. Partial differential is, it's obvious. Differentiation, once you know differentiation, partial differentiation is simple. Linearization, once you know partial differentiation and this formula, linearization is simple. Just by hearing that formula and substituting in that, that's all. So these are the two topics. One, the partial differential of function of two variables, partial differential of function of three variables, and linearization. So I am stopping here for now. In the next video, I will be talking about Laplace's equation, or the higher areas that involve differentiation of functions of two variables. Okay.